Good morning. We're pleased to be in a discussion with Abhishek Saha today relative to droplet travel and a collision rate theory, which is quite interesting. And Abhishek, would you like to give us a little bit of your background, if you would, kind of walk us all the way around the world that you've been here, Central Florida, India, and so forth. Give us a little of that background, if you would.
Sure. First of all, thanks for having me on your show, Bob. Yes, it's I have actually moved around quite a bit in the last 10, 15 years. So I'm originally from India. I did my undergrad in India. Then I worked for an automotive company called Tata Motors for about 2 years. Then I moved to Central Florida, University of Central Florida, actually, to do my PhD. And after doing PhD over there, I moved to New Jersey, Princeton, where I was about 6 years as a postdoc and then a research staff. Then in 2018, I moved to University of California, San Diego as an assistant professor, where I am right now.
Well, that's interesting. Well, you spent 2 more years at Princeton than I did, and it's 6 more years in engineering. I was in a school that no longer has a name. It was called the Woodrow Wilson School.
I know that school very well because I had a couple of my colleagues working there too.
Oh, did you? Yeah, but they've eliminated the name. I don't know what they call it now, but it's no longer the Woodrow Wilson School. So yeah. So that's interesting. Well, you've been to a lot of places where COVID is. Now big in California, it was big in Florida, and there's a big challenge now in India. So it's
right.
Yeah, it's very important that we get the problem solved. So
right.
It's certainly a very interesting project that you've been involved in. I guess the first question would be, tell us a little bit about this international team and this, how you're grouping together on this collision rate theory.
Sure. So actually, that's a very important point here, because the work we have been doing is actually truly in a true sense of collaborative work. So first of all, the team members. So there are 3 institutes involved. Other than UC San Diego, it was University of Toronto, and then Indian Institute of Science. Now, 3 members from these universities, we know actually each other very well. How? Okay, the person who actually initially started thinking about it was Professor Satyapurva Chaudhary from University of Toronto. He happens to be my undergraduate classmate, and then we also spent 1 year together in same research group in Princeton.
Oh, okay.
So, and then the other person, the Professor Saptarshi Basu, he is my PhD advisor. So he was in University of Central Florida before, and then he moved to India. And it happens to be that Professor Chaudhary and Professor Basu, they are PhD group mates. So they did their PhDs from the same department, same advisor actually. So you see, you know each other very well, and then
right.
that was actually one of the main, when we started working on this thing, because each of us brings some kind of expertise to the project, but because we knew each other very well, the things moved much faster and much cohesively. And so that's the background of the team. And it started when we were locking down everything. Then I remember I was going out, I was driving somewhere, I think, and then I received a call from Professor Chaudhary. He said, "Yeah, we had everything is closing down, but we should start thinking about doing something which can help understand this COVID spread." And he has a tremendous experience with the combustion and the chemical kinetics kind of problems. I have experience on both droplets mainly, and then also some experience with the chemical modeling. And Professor Basu also has a lot of experience with the droplets. So we started talking about among each other, and then eventually we started moving towards like what we see in the paper right now, that how we can take these models which we know from individual or individual branches of sciences, for example chemical kinetics, or even droplets, and then we can bring them together to actually explain how this disease spread through droplets and how human interaction comes an important role to it.
Yeah, that's certainly very interesting, and I think this diagram is probably a good point of reference to kind of walk us through this collision rate theory and how everything comes together with what you're doing here.
That's true. So there are two parts to it. So one is we knew, when we sneeze or cough or talk or breathe, any event, we have some droplets coming out, right? And if you are infected, definitely these droplets are going to contain some virus. Now, how these droplets travel in air and how these viruses, live inside a droplet, that becomes an important part of this whole problem, right? Now, on the other hand, you also need to consider how to model this, these droplets which is coming out from an, infected person, how it is going to interact with the people around you who are supposed to be healthy, and if these droplets land on them or they inhale these droplets, they could be, at the risk of being infected as well. So then you see that's why the diagram is this way, that if you take the population, there are, in general, especially when you start, when COVID started spreading, you only have very few people who are actually infected, and that we, shown in terms of red people in this whole population, right? Now, then again down two branches, left and right. Right side shows the interaction. That is, when a person is actually, or infected person is actually walking around or moving around, when they inject a cloud of droplet through their respiratory veins, these droplet clouds are going to interact with these healthy people around. This is where we actually brought in the concept of molecular collision theory. We said that, just like in chemical reactions, the reaction rates, they depend on how frequently these reactant molecules are colliding. Similarly, over here, we can consider it this: the cloud is going to collide. This is a droplet cloud coming off an infected person that is going to collide with some healthy person, right?
Right.
So in a way, it is exactly like chemical reaction, that how frequently these clouds are going to collide with healthy people are going to dictate how fast the disease can spread. Okay, so that's basically where the molecular collision theory comes, and it gives us some coefficient or reaction rates. Okay, now these reaction rates are significantly dependent on droplet physics. How? Let's say I breathe, right? And then there are droplets. These droplets are going to evaporate with time, and as they evaporate, they are going to be smaller and smaller. And during this evaporation process, they are going to travel, right? They're going to go, depending on the droplet size and also the climate or weather around you, they can travel farther or shorter distances. So this becomes an input parameter for the chemical kinetics or the chemical molecular collision model. Okay, and this droplet part is shown in the left side of this figure. That when a person coughs, if the droplet is too large, they're going to settle on the ground. And if they're small, they're going to sustain in the air, and then it will evaporate, they're going to travel. And we included this droplet physics using, coupled equations for heat and mass transfer, and as well as aerodynamics, because the droplets are going to travel in air. So, and then eventually this left-hand side of this this droplet physics and the right-hand side of the collision theory, they came together and give us a time-dependent variable which we can predict like how far and how fast these infections can happen. Okay, now I must include here one point, that is, of course, we in this particular work we did have some assumptions. For example, first we didn't consider any of the masks. We are considering people are simply coughing and the droplets are coming freely from their mouth or nasal cavity. And at the same time, we didn't consider any social effects. That means how this interaction of the people to people, or this molecular collision analogy, this rate will change depending on how many people are available around you. Of course, if you have social distancing, then these effects needs to be considered. The rates will change. But for the first part of the model, we didn't consider any of this. Of course, the latter can be included because the rate coefficient will just depend on this, how frequently this collision happens. But there is a parameter in our model that you can actually change depending on what you think is how much of the population is actually outside, and that will give you a better understanding on, or better measure of how fast the disease can spread.
Mm-hmm. Okay. Yeah, very, very interesting.
Yeah, and it is the major why we think we actually made a breakthrough is this model. If you look at the model from the very fundamental point of view, this is somewhat like what people use in epidemiology prediction called SIR model, that is susceptible, infected, and recovered model. So it is not much different in terms of the model itself. But what is different is in SIR model, what you do, you first create a differential equations, and then you feed the solution of the equation with the data you have.
Mm-hmm.
Let's say you have data for influenza, you're going to use that to predict, okay, what is going to happen 10 days, 15 days, 30 days down the line, right? So in essence, there is not much physical intuition to that. It basically what is happening now, you are going to use that to if you have a data for event A, you are going to predict using the same data, try to predict what happens in event B, right? But in this model, everything there comes from some sound physical, which is called first principle, physical law of first principle. We account, we can literally put numbers to each and every aspects or every terms you have in this model. They're not like you don't need a data to fit that. So that's where I think the importance is. And eventually, if we can do that for different aspect of this disease spread, that is a first principle based model, then it could be not only for COVID or any future outbreak can be predicted much better.
Yeah, I agree with you 100%. I think what's been lacking here is a mathematical approach like this. There's been too much just reliance on evidence that without the analysis of how something happened. People are finding COVID here and there, and they're making decisions based not on a logical decision of how something got where it was, but just the fact that it did. And so I think that that we really do need this kind of approach, and I can see it being applied. We were just analyzing what happens in a mall setting, a shopping mall, where you've got emitters, you've got HVAC systems, and of course you have certain numbers of people. But even within one HVAC system distance, you have everything you're talking about here. So I would think it certainly got a use generally for broader population implications, but certainly in a lot of specific instances as well.
That's true. That's absolutely true.
Now, tell us a little bit about what your findings are relative to the cold and humid climates, then, as opposed to the dry.
Right. So as I mentioned, that droplet physics becomes an important part, especially how long the droplets are going to last and how far they are going to travel. Now, so these droplets are going to come out, and then they're going to be sustaining in the air for a while, and during that process, they're going to evaporate. They're going to either see a colder or hotter environment around you, and they're going to the water part of the droplet are going to evaporate, right? So what we found, if you go to cold and dry weather, cold and humid weather, that's the extreme actually. So because it is cold, outside cold, then the heat transfer from the surrounding is much lower.
Mm-hmm.
So, and that actually reduces the evaporation rate, right? And on top of that, if the humidity is also high outside, then it gives you, the evaporation becomes even more difficult because the diffusion process of the vapor diffusion becomes very, very slow. So it turns out, during that process, the droplet, even as medium-sized droplet, will last very long time. On the contrast, if you go to a hot weather and also hot and dry weather, let's say desert weather, right? So where you would, because the temperature outside is very high and the humidity is also very low, the heat transfer and the mass transfer will significantly higher, and that basically makes the droplet to be much smaller and reduce faster. Now, what eventually it boils down to is basically how long the droplet can travel, and how long how far the droplet can travel. That depends on how long the droplets are surviving in the air, and that will definitely connect to how the weather itself. So if you go to cold and humid weather, then it becomes, the droplet life becomes longer, so it can travel even farther. And on the dry and hotter weather, the travel distance as well as travel time becomes smaller, so they actually tend to evaporate faster. Okay. Now, I should add one more thing here. In this particular model, which only used droplet, we didn't use any aerosol kind of transition. And what I mean by that is, we know the droplet are going to evaporate, but eventually if it evaporates, it is going to form a very small particle-like structure where not much liquid you have, but mostly you have the virus and some salt remaining. We call nuclei. Now, those nuclei can also travel and transmit disease, which is still under investigation. And so for this particular model, we didn't include that. So it is only based on the droplets.
But you will be including the nuclei models in the future.
That's right. As a matter of fact, we just finishing working on the second paper, which is a better version of this model, which has more predictive capability, as well as it includes the effect of nuclei and how nuclei can cause this transmission to longer transmission process. Basically, after the droplet are gone, you still have nuclei, and if virus stays within the nuclei as active, then of course the spreading capability of this nuclei can be significant compared to the droplet ones.
And that would confirm, a lot of the incidental information that they're finding in China, for instance, that a lot of these cough droplets, let's say, that eventually end up on the ground and dry, and you have these, salt particles, so to speak, become airborne again, and that in the changing room, for instance, in some of these Chinese hospitals, the viruses in the air are higher than they are in some of the isolation rooms, and obviously just the mechanical aspects of changing a garment and flexing it and so forth is causing these to be aerolized again. So so it's interesting that you'll be doing that as well, and
right.
And so with that now, I would like to just discuss with you what and whether you'll be able to do something on that as well, which is take this person with the mask here. I mean, this person in red here, and let's say that he is wearing a very efficient mask, and therefore, if he coughs and sneezes into that mask, there shouldn't be any appreciable virus that moves through it. On the other hand, if he's just wearing a cloth mask with pretty large openings, much larger certainly than a virus in a small, 5 micron droplet would need, doesn't it stand to reason that he is going to be, as he breathes in and out, you've got this flow of air passing around this droplet on the inside of that mask, and I see absolutely no reason it's just not going to all end up as aerosols and need to be then taken into account in a model such as yours.
That's correct. So the way, the input to the model here is what is the droplet size distribution or the aerosol size distributions coming out of a person, right? And when you say that, it basically, if you have a protection, whatever the protection efficiency is, based on that, the droplet size distributions with virus, of course, the coming out of the other side of the protection will be input to the model, right? Now, of course, if we see in the paper that if you do use something like N95 mask, it is significantly lower, right? And compared to the what we have viral loading in unmasked person what is coming out, and compared to that, if we consider N95, it reduces significantly lower. But at the same time, I do know of a couple of studies where they are showing that okay, yeah, if you do have cloth mask, the protection is not that good, because not only it doesn't cover the virus, but also because the fiber holes or a gap in the fibers are so large that eventually you are going to create maybe like a 20% only reduction in 20-30% reduction in the numbers, right? Now that's other side, you still have a giant amount of, or large amount of virus coming out, which still can be transmitted the way for an uncovered person.
Yeah, it's in fact, I was president of a scrubber, an air pollution scrubber company, and we spent 15 years trying to develop what we call it a liquid encapsulation scrubber. But you had a very fine screen, and we sprayed droplets with surfactant onto the back of the screen, and then the dirty air went through the screen and converted the whole gas mass of gas or air into very, very fine toothpaste-looking bubbles. And it occurs to me that a cloth mask is like our foam scrubber generator, that it takes a larger droplet and just converts it into a lot of small droplets. So the implications here, are certainly huge. And in fact, I just we'll go down to that for a minute. The a very rough, calculation that people use, and I think it's changing, is that if you aren't wearing a mask, 60% of the transmission may be through coughs and sneezes, and only 20% through contact or airborne. But if you use an N95 mask, your total will reduce from the 100% maybe down to 12% by one rough calculation. On the other hand, if you use the cloth mask, the amount that from an initial cough will go way down, but the amount that would be then airborne will be much higher than otherwise, and therefore, the ultimate effect is that you're going to be transmitting droplets a lot farther than if you didn't have a mask at all, and then of course the total reduction is not that great because you've got you're providing an aerosol generator there, and everything fits the logic here except the experience that where they do wear cloth masks, they seem to have lower infection rates. And I think what may explain that is if you're a few feet from somebody who coughs or sneezes, you might be inhaling millions of virus particles, whereas if he coughs into a cloth mask and you're 50 feet away, you may only inhale a few hundred or viral particles, and you may become asymptomatic. So the fact that 90% of all the people who are infected are asymptomatic or only have light symptoms, and they haven't even been, for instance, in the United States here, they're estimating that 90% of the infections haven't been even, so instead of 3 million, we've got 30 million people walking around that have actually had the virus. But what might explain it is then that that these are aerosols that are smaller and possibly are less harmful. But in any case, it would seem to very logical that the cloth masks are aerosol generators, and it would seem with that could be one of the things that you would want to be putting into your models to the extent that could happen. And certainly someone like yourself who's is functioning on droplets, would be in the best position to say, okay, if you've got something like the inner surface of a mask, which is holding that droplet, to what extent is that droplet going to go through and continue on this voyage in possibly starting out even as much smaller droplets, but taking that same path.
That's absolutely true. If it is really the problem, if you're wearing the mask, which is kind of what you call shifting the distribution, like if you are breathing out, like you have a size of droplet distributions. Now if your mask is filtering everything out, it's perfect, which apparently what N95 does. But if you're using cloth mask and if it eventually just shifts the larger droplets to a smaller droplet, it's still the virus is still there, then it doesn't help the cause. In fact, if the droplet are small, then they can actually stay in the air for longer time, because if the larger droplets, what basically happens due to gravity, they actually fall on the ground. But if you are taking the same, say, one large droplet and you're breaking it into smaller, say 4 or 5 smaller droplets, and then you're pushing in the air, then you are actually making it worse, because then the droplets are going to stay in the air for a longer time. They won't settle on the ground, right? So it is actually a very important aspect. If it is really the case, then we need to know like how the shift happens. If you have a cloth mask, how the droplet size distribution changes from before and after the mask, right? And then if we know this distribution, then we can use that in the model as an input to the model parameter, and then it will show us significant difference. That's my feeling. That is because now we see that larger droplets fall. If you don't have larger droplets, everything is small droplet, but still the number of virus is the same, then we do see that could create a significant shift.
Yeah, I would imagine in your laboratories and things, to do what we did with our foam scrubber thing. You spray droplets onto the back of a screen, and then you measure the size of the aerosols, downstream of the generator, so to speak, there. So, but I have no doubt that just the velocity in breathing is enough to cause those droplets to certainly evaporate, but probably even to be mechanically pushed through the mask in smaller quantities. And some of the research, the evidence, people are puzzled that they've been measuring viruses inside and outside of cloth masks. And in this one study, they couldn't figure out why all the viruses they measured were on the outside of the mask and there were none on the inside. And they had all sorts of speculations, but they were accused of not being accurate in the research. And then they said, well, we swabbed the outside of the mask so that if we did push any we swabbed the outside first, so we make sure that we weren't just taking the inside and pushing the viruses through. So there'd be no reason that wouldn't have been an accurate measurement of where the viruses eventually landed. And of course, if you've got none on the inside of the mask, some on the outside, the obvious question is what happened to most of them, and most of them probably ended up as aerosols. So I think what you're doing is certainly very, very important. How are you proceeding from here? What's your how are you moving forward to? Because it's a pretty ambitious project to put all this together.
Right. So right now, as I mentioned, that the second part of this model is coming out very soon. So what we did is as I mentioned, that we started including the effect of nuclei, because see what you are saying, that effect of smaller droplets on nuclei to capture in the model. First, we need to establish the model to include the effect of nuclei, and these nuclei behave somewhat differently than droplets, because they don't evaporate anymore. They're very small, so they just float around, right? So first we need to account them to this model. So that's we have been doing, since we published the paper, we have been working on that, and we think we are in a good position right now to get that paper out. So we are doing in the process, we are finalizing few things. So after that, the idea is will it be, if our model is very significantly robust, then we need to do some measurements, for example, how the droplet clouds move and how they travel in air, and get some physical evidence so that we can actually tie up with those information in our model as well. So that has been, major direction. Now, things are not that easy because our labs are not officially open because of the lockdown. We can only operate in a very reduced capacity. Modeling work is not that problem because you can still stay at home and then work on that. But when it comes to doing large scale experiments or involved experiments where we need multiple people, we still are a little bit restricted on that. So, but we had three of us, me from UCSD, then Professor Chaudhary from U Toronto, and then Professor Basu from Indian Institute of Science. We're still thinking of how we can leverage each of our ideas and our capacities in our respective labs to make this model even better, and then eventually go to the point that, okay, yes, now we are ready with all the all the aspects which you can cover, and of course with some parameters which you can change depending on the situation you are trying to model. So you are trying to model in a small room or big malls, as you mentioned. Those things will change. So we will give you those parameters that you can change room dimensions or locations, weather, etc., and you can predict that what would happen to the disease or how it could spread.
Even without the experiments, it would seem that with all your droplet experience and so forth there, that you could, analyze what would happen to a droplet on the inside of a mask, subject to the exhalation velocity, normally that you're going to find in a cloth mask, over time. And I don't see how they're not going to all end up as aerosols, but I think nobody seems to have looked at this. And in fact, it seems amazing to me. Everybody's, oh, well, the mask caught the cough droplet, therefore it's gone. Well, it's not gone. It's on the inside of the mask. And unless somebody takes the mask off immediately and throws it away, if they wear it for another few hours, they're generating aerosols the whole time. So it would seem to lend itself to modeling pretty well, would it not?
It is possible, but it is it is a little bit more involved, because the way you model masks are actually porous media. So and of course when you change the mask quality, the pore sizes will change roughly. Right. So what you need to do then, the model that if you have a jet which is coming on one side of this porous media with some sort of droplets, and you monitor how these droplets are being transported through these pores on the other side, right? You see they actually come out, or they basically get trapped, right? But this modeling is not very simple, because anything to do with porous media, because they're when you go inside the pores, because they're multidimensional motion and as well as randomness in the pores distribution. So it is just not simply one modeling. Of course, you can get some scaling analysis done, but that wouldn't give us that accuracy, and we what we need to have some accuracy in the measurement, so that we really can say, okay, this is what is coming out on the other side, right? So yes, it is possible, but it is a little bit more involved than what we have done so far, because whatever we have done is totally mathematical modeling, but the other part which I'm talking about, it perhaps needs a simulation where you can do CFD simulations with the flow and droplets through the porous media.
Yeah, and then one final question for you here is, we're talking a function of both mechanical velocity that might drive separate the droplet into smaller droplets, but also just plain evaporation, right? As that breath surrounds and moves over that droplet and then out through the mask, it's going to continue to, unless it's completely saturated air, is going to continue to increase the evaporation of that larger droplet into smaller droplets, or one or more, would it not?
Yes, that's true. I mean, I can assume that, I haven't looked at this, but I can assume the droplets which are deposited on the, front of the mask directly from our breathing, right, or sneezing or coughing, those large droplets will evaporate, right?
Yeah, yeah,
Now, but the question remains, what we need to know that if it does deposit and then evaporates, then what happens to the nuclei? Do they have, if the pores are large, then they will come through, right? But so that's the part I was talking about. That if you think about what is, depending on pore size, what size of particles or droplets can come out through and you can do that through simulation, then you will get a particular idea that if the droplet evaporates and becomes smaller than this size, it is not going to be on the mask anymore. It is going to transmit through the mask.
right, right. And the various different, masks they have, what their efficiency is on particles, say 3 microns in size or something like that. But between the pore fit and the pore filter media, most of these masks are probably anything 3 microns in size. Most of it's probably going through rather than being captured. So uh, I think that would substantiate the theory that you're eventually going to create aerosols from these cough droplets.
Yeah, that's highly possible. If pores are large enough, then of course there's a high chance that the particles or nuclei, after evaporation of the droplets, they could pass through.
And when you think about it, if in fact instead of 60% being cough droplets that are not going anywhere, if most of it ends up as aerosols, that you could explain why there's been so much problem right in California and other places to to vanquish COVID, and that so I think the work that you're doing is certainly how the starting point. You've got to come up with mathematical approaches like this, and then just put in the different parameters and variables and take it from there. So I commend you on the work that you're doing there. In terms of working with other organizations, are you then planning to work with other research organizations to take this farther?
That's eventually that's a plan. So once we have good enough or large enough model which we can use actually for prediction purposes, then we hope we will approach to some groups who are actually forefront of this prediction, right? Because we are not, first of all, we are not biologists. We don't do anything on virus life or how they evolve within droplets or nuclei. We don't have those information. We don't have those expertise. And at the same time, we are not forefront of what people who are predicting the spread, right? Because the people who do that, they are mostly epidemiologists.
Right.
What we do is mostly from the physical point of view or the physics point of view, we can establish the models which are sound based on physics, which we actually happening in a micro scale, and then we can put it to use by collaborating with those folks from either from epidemiology groups or from biology groups. They can use our model, and then they say that okay, now this model needs something like more from us. Then we can go back and then to the drawing board and change certain things. So yes, so in a in a way, we do want to collaborate with others, especially in the working in the other fields, not like in mechanical or aerospace engineering, mostly for epidemiology fields, and we want to see how they can use our model to improve the prediction capability.
Yeah, and I do think what you're doing is what's been lacking in the industry because a lot of this is done based on experience of and epidemiology and so forth rather than on the basic physics of what's happening. And so something as basic as what happens to a droplet on the inside of an inefficient mask hasn't even been addressed, which to me is just incredible that we're at this late stage here and it hasn't been addressed. But also what you're doing seems to be cutting edge which I think is another illustration that that there's a lot of value in the approach that you're taking here. And so I think we're going to want to follow your achievements as you go along there. We'll be providing this YouTube to others, and we would certainly encourage them to contact you. And we certainly hope that you'll keep us informed with any insights. And when you come out with this second model, we'd like to learn about it as well.
Absolutely, absolutely. Thanks for spreading these words. Of course, yeah. But three of us we're working together, and then if you get anything from any of us, if you have any information on these models, we will be happy to provide. Either contact me or Professor Chaudhary from Toronto or Professor Basu from Indian Institute of Science.
Well, very good. Well, Abhishek, thank you very much for the interview today, and we'll look forward to working with you in the future.
Thank you, Bob.
Okay, thanks. Bye now.